Bam! Mr. Tarou. In this algebra lesson, we're going to be doing 4 examples of trying to come up with an equation from a table of values. Or your algebra book or pre-algebra book might be calling this a process, an input-output table. But we're going to be looking at some input values, independent values, explanatory variables, or values, and trying to come up with some output values, or our dependent values, or our explanatory and response value. There's all kinds of vocabulary and names we use for these numerical values that we're going to put into some kind of process or equation that gives us these output values. And we're going to be talking about first differences, second differences, and through these 4 examples, they're going to step up in difficulty as we go. And my algebra students this year are really having a struggle with, and it is difficult to try and come up with some kind of an equation that turns all of these input values, or you might be seeing these as your x's, and creating y values. Now, as we look at these tables, we might be noticing some patterns that create the numbers down the column, and sometimes those patterns are useful, and sometimes we just need to play with the numbers, or arithmetic, or addition, subtraction, multiplication, and division, and just keep trying different things until we see something that works. And like we have here in the first example, when this process or equation or function only has one algebraic arithmetic or mathematical step, it might see the pattern relatively quickly. Like when we see what math operation is going to turn a 4 into a 12, a 6 into 18, a 10 into 30, and 17 into 51, you might already be seeing a pattern. And, if not, think about addition, like 4 plus 8 is going to give us 12, but is that same arithmetic or mathematical step going to work on the second line? Well, 6 plus 8 is only going to be equal to 14, so while 4 plus 8 is equal to 12, so we've found a pattern, if you will, or a mathematical process for the first line. That same mathematical process does not work for the second line. And we're looking for the same process, the same equation to work for every one of the lines in our table. So maybe we don't see, or that addition of 8 doesn't work, but okay, we have addition, subtraction, multiplication, and division. Now, addition and subtraction are kind of the same thing. You're just moving once left or right on the number line, and multiplication and division are kind of the same process as well. And if you're looking for, well, these numbers are getting bigger, so we're probably or possibly multiplying by something larger than 1, let's take a look at 12 divided by 4. Well, 12 divided by 4 comes out to be 3. And 18 divided by 6, well, that comes out to be 3. And 30 divided by 10, well, now that comes out to be 3 as well. So I'm taking kind of like the numbers that I already have and work backwards, if you will, to find the process, and I'm doing this division, and through that division I see that I keep getting the same ratio of 3. Well, that means that if I'm finding this 3 through division, then actually to go from 4 to 12, I want to do the inverse math operation, which is actually multiply. So 4 times 3, well, that does equal to 12, and that line checks. And we have 6 times 3, that's going to come out to be 18. Well, that was our output value. We have 10 times 3, which is equal to, not 18, but equals to 30. So far it seems like this ratio of 3 is definitely working. Now, if we want to check it again, we have 17 times 3. Well, let's see here. 17 times 3. Well, if you want to do this in terms of mental math, we might be able to say 3 times 17. If you've talked about learning the distributive property recently, we might think of this as 3 times 10 plus 7, because that's the tens place, and there's 1 10, and that's the ones place. Well, we have 3 times 10 is equal to 30, and we have 3 times 7 is equal to 21. Well, 30 plus 21 is equal to 51. The same, when I do my mental math, I always go left to right. If you were working out sort of more of a traditional method of multiplication, 3 times 7 is 21, carry over the 2, 3 times 1 is 3 plus 2 is that same answer of 51. And it looks like we've got a process. When every single line of this table, we're just simply taking the input value, the independent variable, the x, and multiplying those by 3, and we are matching all of the output table values in our tables. So I'm thinking about all the vocabulary that my algebra book uses. It uses process and it uses equation or the words function. So the output is going to be equal to, because of course it's the answer, the input value times 3. Now when we write our algebraic expressions, a lot of times we like to put our coefficients in the front of the variable. And indeed, multiplication is commutative. That means the order of the multiplication does not make a difference, like 2 times 5 is 10, and 5 times 2 is also equal to 10. So I can rewrite this as the output is equal to 3i, or your book might be writing y is equal to 3x if your labels up here are x and y, instead of I and O for input, like my book I'm using currently likes to do. Now over here in green, we've got 1, 2, 3, 4, 5, and our values are 0, 3, 8, 15, and 24. And when you're first starting to work with these problems about coming up with equations from tables, quite a few in the beginning will just use one math operation like we had here, where it was just simply a multiplication of 3. So you might be going, well, let's see, 1 becomes a 0, so maybe it's 1 minus 1 is 0, but then 2 minus 1 is equal to 1, but our answer over here is actually 3. It's actually bigger. So minusing by 1 doesn't do anything. Well, let's see. If we look at the second line, maybe we can get 2 to be 3 by multiplying it by 2 and then subtracting 1. So we have 2 times 2 is equal to 4, minus 1 is equal to 3. Okay, so that worked. Let's see if it works in the next line. We have 3 times 2. Well, that's going to be 6. We're going to subtract from 1. Try and use the same process we did up here. 3 times 2 is equal to 6, and 6 minus 1 is equal to 5. So, okay, that's not working either. For the second line, I tried multiplying by 2 and getting 4, and then subtracting 1 and getting 3. So I found a process that worked for the second line, but it's not working for the third line. And our process or equation has to work across each line of this table. It can't just work once or twice. So this one is a little bit difficult. And the reason why it's difficult is because I know that our process, our equation, is going to involve 2 mathematical steps, and that's always a little bit more complicated to figure out. So I'm going to give you a little bit of a tip. Especially in the beginning of doing these types of problems, they tend to be what's called linear functions, which means our highest exponent is 1, or they might possibly be quadratics, or an equation that has an exponent of 2. Now here's how you can check that. We got it pretty nice over here in the fact that our input values are all going up by a value of 1. They're not jumping all over the place. If this was like 1 and 5 and 6 and then 10 and the values along the input column are jumping around a lot, then really that increases the difficulty of these problems. But here we have a nice pattern of increasing by 1. So since this is increasing by a consistent value, in this case specifically 1, we're going to come over here to the other side and we're going to look at what's happening over here. If we back subtract this, 3 minus 0 is equal to an addition of 3. And 8 minus 3 is an addition of 5. And 15 minus 8, I'm going like from the higher values of input or x, and I'm working my way up. 15 minus 8 is equal to 7. And then 24 minus 15 is equal to 9. And again, because my input column here is increasing by a nice value of just consistently 1, what this is called over here is my first differences. Okay, and my first differences are not the same. But if I look at my first differences here, 3, 5, 7, and 9, while they're not the same values, I'm actually starting to notice a pattern over here, which is, well, now if I look at those differences again, 5 minus 3 is an addition of 2, and 7 minus 5 is an addition of 2, and 9 minus 7 is an addition of 2. Well, look at here. I've taken, again, I've got that consistent growth or increase of my input values of 1. I've back subtracted all my y values, and I don't have a list of numbers that are all the same, but if I look at my second differences, I do. My second differences are constant. Therefore, my equation is going to involve a power of 2, or a squaring of a number. That is a good thing. So now I know that I can take these values of 1, 2, 3, 4, 5. Let's square them and see what happens. Well, when I square each of these input values, again, because I'm thinking there's a power, I know there's a power of 2, because my second differences are constant, we get 1 squared is equal to 1. That's kind of where we started from. We've got 2 squared is equal to 4. 3 squared is 9. 4 squared, 4 times 4, is equal to 16. And 5 squared is 25. We're working our way towards the input values over to those corresponding output values. Now look at the comparison here. 1, 0, 4, 3, 9, 8. Comparison through subtraction shows that each of my numbers are now just one value too big. So if I come through here and say, you know what, I'm going to subtract 1 from all of these answers, and look at there. I have found a process that gives me, for every single one of these input values, the output value. 1 minus 1 is 0, 4 minus 1 is 3, 9 minus 1 is 8, and I'm actually checking what I believe is I'm actually creating that process and kind of actually checking at the same time. What's the equation? Well, the equation is coming from that repeated process that you're going through with the arithmetic. Every single one of these lines has got the input value squared. So the output is equal to the input, or y equals x, power of 2, every single one of those. And after we squared all of the output, or squared all the input values, excuse me, we had to just simply subtract 1 on every single one of those lines, and we had an output value that checked. So minus 1. And you'll see square, square, square. Okay, the input value is being squared. Every single line I had to subtract by 1. That is my formula. I can see it through the repetition that's in each one of these lines of arithmetic. And that's our first 2 examples. We got not too much, but 2 more coming up right now. So for our third example, we've got this table here. And this table is a little bit more of a step up in difficulty, or maybe, I don't know, maybe you see the pattern right away. But we have 1, and then we jump up to 3, 4, 5. So we have a nice consistent, and it doesn't have to be necessarily a change of 1 for me to say we have a nice consistent increase, and helps us in identifying the pattern, but that it's the same. It might be 3, 5, 7. But as long as we have a consistent growth a little bit along the x-axis, then we're, or the input or the x column, it can ease the difficulty of these questions a little bit. But they're always going to be, until you do a lot of practice, I think you'll probably find it to be a little bit difficult. So, okay. Well, we got 1 times 4 is equal to 4. But when we try doing 3 times 4, we get 12, and the answer is supposed to be 16. So while multiplying by 4 works for the first line, it does not work for the second one. You could say maybe add by 3. 1 plus 3 is 4, but 3 plus 3, again, is not equal to 16. And considering how quickly these numbers are becoming large, this is only 3 bigger, this is 13 bigger, this is 23 units bigger. I feel like there's a little bit of multiplication going on in the process that's creating all of these x's, turning all these values of x into these values of y. So let's focus in here a little bit. We've got 3, 4, 5, that nice one-step increments in the x column. And if we look at that and we go 22 minus 16, well, that is an increase of 6. And if you back subtract on the 22 and the 28, well, 28, the number farther down the y column, matching up with the larger value of x, we get 28 minus 22 is also equal to 6. So there might be that consistent addition of 6 on the table, but I'm going to actually add a few lines to this table to test whether or not maybe I can see that this increment of 6 is showing up as we have the values of x increase by 1. So I'm going to fill in a value of 2, and I'm also going to include a 0 line in here, and I'm going to talk about how that might help you as well. Now with the blue, I'm going to highlight these numbers that I'm adding into the table, the 0 and the 2. The 5 and the 10 are so far apart. I'm just going to work with these first now 6 lines and see if I can't see a pattern that might be working. Now remember, we had the plus 6 and the plus 6 going between 16 and 22 and 22 and 28. Now if I'm working my way down where my values of x are increasing by 1, then as I work my way back up, right, because I think I have this consistent pattern of plusing 6. Well, if I back up 28 minus 6, I'm going to do the inverse math operation because I'm going up, or sort of like going up, allowing those x values to now decrease by 1 instead of kind of going down the column and increasing by 1. 28 minus 6 is 22. 22 minus 6 is 16. 16, sort of, I'm going to go this way, minus 6 is equal to 10. 10 minus 6 is equal to 4. I had that before, right? Right over here. Now if I back up again, 4 minus 6 is going to be equal to negative 2. Okay, so why do I want to go back all the way and include a 0 line? I found this to be a little bit, kind of helpful as I work with these problems with my algebra kids this year. There's really basically just 4 simple math functions: addition, subtraction, multiplication, and division. Well, multiplication and division, when you multiply by 0, anything times 0 is equal to 0. So the only math process that's going to make 0 become negative 2 is a subtraction of 2. Our equation, because of this negative 2, our equation, our process, has a subtraction of 2, or an addition of negative 2. Now check this out. We also have a 4 plus 6 is equal to 10, and 10 plus 16 plus 6 is equal to 16. So I've expanded the table a little bit, and I have my values of x increasing by 1. And with that consistent increasing by 1 in my x column, my input column, I'm noticing that the first time I back subtract 28 minus 22 again, 22 minus 16, 16 minus 10, the first set of differences is constant. And identifying that the first differences are constant is not going to be a useful pattern unless we see that consistent increase in our x column. But since our first differences are constant, therefore the equation is going to be linear. And I like to talk to my kids about, a constant, just as you go down right from the very first set of numbers, if you see a consistent repetition, repeated adding of 6, or repeatedly adding by anything, repeated addition is shown or done more quickly through the mathematical operation of multiplication. Repeated addition is basically multiplication. So it looks like from our 0 line, giving us an answer of negative 2, our equation has some kind of subtraction of 2. And I believe we have some kind of repeatedly adding by 6. So let's see here for a second. If we give this a shot, how about we say that if this is x and this is y, that we have y is equal to 6x minus 2. Let's see if that works. We've got 0, like right here. We have 6 times 0 minus 2. We have 6 times 1 minus 2. We have 6 times 2 minus 2. I'm taking each of these values of x and plugging it into what we think might be the equation. We have 6 times 3, there's the x right there, 6 times 3, the 3 there, minus 2, and so on, and so on. And if we check this, we have 6 times 0 is 0 minus 2. 0 minus 2 is negative 2. We have 6 times 1, which is 6 minus 2. Well, that is 4. We have 6 times 2, which is 12. So we're doing really good here. Minus 2 is equal to 10. And this pattern needs to not work for just 1 or 2 lines, but it needs to work for every single one of them. And indeed, as we go down the list, 6 times 4 is 24, minus 2 is equal to 22. And see, every single one of these lines has a multiplication of 6, so your equation needs to have that multiplication of 6 in it. Multiplication of 6 to our input value of x. And every single time we had a number that was a little bit bigger than our final answer, it was a little bit bigger by a difference of 2. Again, that 0 line showing that our equation had to have a minus 2 in it. Now, I like this and this is done, but we don't all think exactly the same way. If you change this a little bit in how you're approaching or thinking about the problem, you might go, hey, my 0 line had a subtraction of 2, so our equation, still going with that idea that you had to have a subtraction of 2, you might go, well, what was each of these numbers then? If we subtracted by 2, what was each of these numbers before you subtracted by 2? So let's do like a little before your minus 2 that the 0 line is saying that you had to have had. What number minus 2 is equal to 4? Well, that's 6. What number minus 2 is equal to 10? Kind of going backwards, instead of minusing by 2, you add by 2. That would be equal to 12. And this would be 18. And this would be 24. And this would be 30. And this would be 60. So even if you didn't catch that constant addition of 6, meaning that your repeated addition is multiplication, and oh, by the way, we said that our first differences were constant, so the equation had to be linear. See this y equals 6x to the first, that exponent of 1 on the variable, that's what that linear function means. Well, even if you didn't see that repeated addition of 6 coming up here, you could now go, well, if you at least notice the minus 2, back that out by doing the opposite, which is adding by, or inverse, which is adding by 2. Look at the 1 and the 6, the 2 and the 12, the 3 and the 18. Guess what you would notice? Hopefully, 2 times 6 is 12. 3 times 6 is 18. 4 times 6. And there's sort of like another way that you might notice that you needed to have included that multiplication of 6 in your equation. And that is the end of our third example. We got one more coming up right now. And for our last and final example, I've given you all the tricks that I could maybe really think of at this point that you might see. So I've really mixed this up. My values of x, or my input values, my values of y here. My values of x are kind of jumping all over the place. We go 0, 3, 9, negative 7, negative 2. Really taken away that consistent growth of the x. We've already talked about first and second differences. If your first differences are constant, it's going to be linear. If your second differences are constant, it's going to be a quadratic or have an exponent of 2, a power of 2. But we can't look at these first and second differences if my values of x are increasing and decreasing and kind of jumping all over the place. So this one, you might just have to play around with the numbers and keep trying different things until you find that process. But we have one helpful little tip or thing we might notice in this table, which is there is a 0 line, right? And the only way you're going to get 0 to become 5 is not by multiplication, not by division, but by adding. So your equation, because chalk down of our 0 line, right there, we have an addition of plus 5. Now we can back that addition out and get a little bit closer to the starting values. If we added, okay, so before our plus 5, we had to add some number by 5 to get 5. What plus 5 is 5? Well, that's going to be 0. What number plus 5 is equal to 2? What number plus 5 is equal to 2? Undoing that addition of 5, we get negative 3. Or maybe you're looking at a number line and there's 2, 1, 0, negative 1, negative 2, negative 3, negative 4. An addition to a 5 is a movement to the right, and I want to move to the right 5 places and get to 2. Well, the opposite is moving in reverse. So if I'm here at 2 going back, that's 1, 2, 3, 4, 5, landing us on, my labeling got a little bit messy there, but landing us on negative 3. What number plus 5 is equal to negative 4? Or going in reverse, negative 4, let's give you another look. Negative 4 minus 5 is equal to negative 9. What number plus 5 is equal to 12? Well, going in reverse, that would be 12 minus 5 is equal to 7. And then finally, what number plus 5 is equal to 7? Well, working our way backwards, then we would be doing subtraction, which is equal to 2. Well, now look at this. Wasn't sure how we were going to turn 0 into 5, 3 into 2, 9 into negative 4, but after we've backed out that addition of 5 by basically going in reverse or subtracting by 5, oh, it's the same number, but we just have a sign change. So we had to have taken all of these input values or values of x and multiplied them by negative 1. And of course we have to remember that a negative times a positive is negative, and a negative times a negative is positive. So every single one of these lines involves a multiplication of negative 1, and every single one of these lines involved an addition of 5. So it looks like our y value is equal to our, or maybe it was O for output, is equal to x, or my input value, times 1, negative 1, and then add by 5. And if you're not, if you want to double check, that's really what you should be doing all the time. We've got, let's do this in red. How about, well, we are kind of already have this here. Negative 1 times negative 2 plus 5. Well, negative 1 times negative 2 is positive 2, plus 5 is equal to 7. And that check with every line in your table is going to work. That is the end of my fourth example. I hope that helps you identify how or what the equations are that are creating the table of values that you're given in Algebra 1. I'm Mr. True. Bang! Go do your homework.